All right, so now we're going to discuss problem solving, how to do it. What's problem solving? It's really, what I consider it, it's translating words into symbols, or maybe English into math. And then once you have a mathematical equation, then you just solve it. Now, in Physics 121, you will see that the math is simple. Where people have trouble is translating the English into the math. And that's the physics, right? Coming up with an equation to solve. So Randy Knight has a wonderful problem-solving strategy. And I'd like you to learn and use this. It maybe at first seems cumbersome, but I guarantee you, if you follow it, if you can do simple mathematics, usually just algebra in 121, you'll get the problem right. So that's what I want to go through. Yeah, I know there's a lot of words. Just keep the faith. All right. So this is the Randy Knight general problem-solving strategy. First thing you want to do is you want to model. And I already talked about that a little bit. Model. It's impossible to treat every detail of a situation. So we're going to simplify the situation with a model that captures the essential features. For example, the object in a mechanics problem is usually represented as a particle. We talked about that. Next, visualize. This is where expert problem solvers put most of their effort. What does it mean to visualize? Well, we're going to learn how to draw something called a pictorial representation. This helps you visualize important aspects of the physics and assess the information you're given. It starts the process of translating the problem into symbols, right? So we're going to spend a lot of time on this pictorial representation because it's probably the most important part. Oh my gosh, look at all that. All right, so drawing a pictorial representation. First thing, draw a motion diagram. Why? Because it develops your intuition for the motion, and especially important, determines whether the signs of V and A are positive or negative. So it's just a tool to help you figure out what's going on and to prevent you from making silly mistakes. Establish a coordinate system. No kidding, right? But hold on. Select your axes and origin to match the motion. For one-dimensional motion, you want either an x-axis, or a y-axis, parallel to the motion. Sketch 3, sketch the situation. Not just any sketch. Show the object at the beginning of the motion, at the end of the motion, and at any point where the character of the motion changes. Now, Randy Knight says, show the object, not just a dot, but very simple drawings are adequate. I just draw a dot, but you do whatever you want to do. Okay, define symbols. Use the sketch to define symbols representing quantities, position, velocity, acceleration, time. Remember, that's it, right? Position, velocity, acceleration, time. There's nothing else for a motion. Okay, here's the important thing. Every variable, so what does this mean? It means, you have to sketch the object at the beginning, at the end, and if something changes. So at these points, beginning, end, and if something changes, you want to have x, v, a, t for every point. Every variable used later in the mathematical solution should be defined on the sketch. And you'll see when we do some examples. Some will have known values, others are initially unknown. But all should be given symbolic names, x, v, a, t, all right? And we'll use subscripts because we might have 2 points, 3 points, who knows what. List all the known information. Make a table of the quantities whose values you can determine from the problem statement, or that can be found quickly with simple geometry or unit conversions. Some quantities are implied by the problem rather than explicitly given. Others are determined by your choice of coordinate system. And then we want to identify what we don't know. We want to identify the desired unknowns. What quantity or quantities will allow you to answer the question? That's kind of important, right? These should have been defined as symbols in step 4. Don't list every unknown, only the ones that you really care about, the ones that answer the question. Okay, all right. So that's drawing the pictorial. This is the important part, honestly. This is so important. You get this right, if you can do simple algebra, you get the problem right. Okay, then use a graphical representation if it's appropriate. Sometimes it will be, sometimes it won't. Go back and forth between the graphical and pictorial, you know, just to whatever you need. Then finally, okay, so look at, first you model, then you visualize. Again, that's where you put most of your effort. And then then you solve. Only after modeling and visualizing are complete is it time to develop a mathematical representation with specific equations that must be solved. All symbols used here should have been defined in the pictorial representation. Now, some people quit there, which is a big mistake. The last step is you want to assess. Is your result believable? Does it have proper units? Does it make sense? So years ago, I gave a physics test, and the students were supposed to find the height of a tree or something. I don't know, something like that, right? And a student came up with height equals, I'll just make this up, minus like 40 meters or something like that. And then what the student did, just took the eraser and did like that. Now think about it. If you come up with a height of a tree to be negative, doesn't that sort of imply that you made a mistake? Well, yeah. Okay. Well, how about this? What would you do here? If you came up with an answer 40, seconds or 40 kilograms, you made a mistake. So, or what if you did something like this, 40,000 meters? That's crazy. So you always want to assess your answers. And this is a good habit to get into, especially for your future career. I mean, if you're a doctor and you make a mistake, you could kill somebody, right? And so this is incredibly important. Assess. Oh yeah, okay. All right, does it have proper units? So whenever you're solving your equations, you should always carry your units, like 4 meters per second or 3 meters per second squared. Because again, what we talked about last time, the units, you should treat them as algebraic quantities. And you should always check if your units make sense. If your units don't make sense, it means you made a mistake, a big mistake. And so you really want to do this, include the units in the equations. And I require you to do it in your problem sets. If you don't put your units in your problem sets, you get points deducted. Because you got to get into this habit, trust me. Okay, so believable, proper units, does it make sense? I think if you worked in a bank, at the end of the day, you're supposed to count, I don't know, it's like sum up everything you did during the day. I mean, if you had a minus and you change it to a plus, you can get fired, right? So just assess, assess, be honest. All right, let's see. All right, so we're going to do an example. So I'm going to do it. All right, so let's see. And I chose this one because I assume hardly anybody in this audience of mine, hardly anybody has probably ever played ice hockey. I have, but anyway. Ice hockey star Bruce Blades is 5 meters from the blue line and gliding toward it at a speed of 4 meters per second. You're 20 meters from the blue line, directly behind Bruce. You want to pass the puck to Bruce. With what speed should you shoot the puck down the ice so that it reaches Bruce exactly as he crosses the blue line? So again, most of you are saying, what's a blue line? What's a puck? Well, that's good. I don't want you to know this stuff. All right. So visualize. This is where the expert problem solvers put most of their effort. So here's my opinion. Read the question twice. If I had $1 for every time a student came to me and said, I didn't know it meant that, and could they get the problem wrong? If you just read it twice, it'll help. So read the problem twice, think about it, and actually visualize it in your head, and then on the whiteboard or your paper. Okay, I'm not going to read it twice. Sorry, I'm a hypocrite. All right, so the first thing you want to do, we kind of want to get a feel for what in the world's going on. So let's just draw what's going on. So the first thing we want to do is draw a motion diagram. Okay, so a blue line. What's a blue line? Well, don't worry about it. But it's something in hockey, okay? So there's a blue line. And it says Bruce is 5 meters from the blue line and going towards it, and you're 20. Okay, great. All right, so let's see. Now notice Bruce is going 4 meters per second. And you notice it's ice. So what's ice? In Physics 121, ice means no friction. So in other words, Bruce is going at a constant speed of 4 meters per second. Now, we're way behind, right? You're way behind, and you have to pass the puck. So obviously the puck is going to, and then you want Bruce and the puck to get here at the same time. So obviously the puck is going to have to go faster than Bruce, right? All right, so let's draw it. So here's Bruce. So it's supposed to be constant, all right? Just pretend. Supposed to be a straight line. All right, so there's Bruce, okay? So there's Bruce. And again, you want to label it. Again, this is just to help you, right? And so we know that Bruce's acceleration is 0 because it's constant speed, constant direction. And this is the start, that's the end. I guess we could label it. All right, now now, second thing. It says you are 20 meters from the blue line, but you want to pass the puck, and we want to know the speed of the puck, so the puck reaches Bruce at the same time. So what's the important thing? You or the puck? The puck. You're irrelevant. All right? So we don't care about you, sorry. So we care about the puck. Yeah, whatever. All right, now the puck has to be going really, really fast, so I'm going to be smart this time, right? Constant speed, though. And you don't have to make perfect scale drawings, you know. All right. So this is the puck. Okay? All right. And again, the puck has A equals 0 also, right? All right. So there you go. That's the motion diagram. So what do you know? Now you know the velocity is positive there. You know that the velocity is positive there. You know that this speed is greater than that speed. You know these are both acceleration equals 0. You know that the puck has to travel more distance than Bruce, and on and on and on. Okay? Yeah, this is the end, right? All right. Okay, so that's the motion diagram. All right, now, okay, let's see how I did. All right? Yeah, okay. So, this is the one in the book, right? Good enough. Okay? So again, all it does is help you think and start figuring stuff out in your head. All right, so we've done that. Now what we want to do is we want to draw the pictorial representation. And this is the key, honestly. If you do this right, you've got to get the problem right. If you can do simple math. So let's do that. Okay, so so we have a couple of questions to ask. You know, when we read the slides a bit ago, we have to draw the beginning point and the end point, and maybe something in the middle if something changes. Well, nothing is changing here, so all we need is beginning and end. Same thing for the puck. We need the beginning and the end, but nothing's changing, right? It's not going faster, it doesn't go slower, it doesn't take a turn or anything like that. So we don't need any intermediate points. Okay, so I'm going to erase this because I need the room. All right, so here we go. All right, so here's our x-axis, because this is one-dimensional motion, right? Here's our blue line. Okay. Now remember, we have to put symbols at every point. Okay, at every point. All right. So, and we gotta choose an origin, right? I mean, this is a one-dimensional coordinate system. So where's your origin going to be? Well, whatever you want. I mean, really, it doesn't matter. It's totally up to you. You can put it here. You can put it here. I mean, you could put it here. It'd be kind of wouldn't be real smart in my opinion, because then you'd have negative. You know, this position would be negative. Put it here. I mean, put it anywhere. But let's just do an easy thing. Let's just put it here. You know. Okay, so let's call this the origin. Okay, there's the origin. Okay, so what's at the origin? The puck. All right. Okay, so So we want, all right, so now look at, there's a puck and there's Bruce, so we got to use subscripts. So we're going to have x puck, velocity puck, a puck, and then we're going to have time. Now, this is the initial point. This is the final point. So I mean, it's totally up to you how you do this. I'm going to say the initial point is 0. All right, so we have x puck 0, velocity puck 0, a puck 0, t 0. And that's all you need, all right? So that's where the puck is at time equals 0. And of course, we're going to say that time equals, and what's initial time? Well, 0, right? I mean, you can say something else, but it'd be kind of difficult. All right, now we want Bruce. So, and I don't really care. I'm not going to make a scale drawing. So same thing. So x Bruce 0, velocity Bruce 0, acceleration Bruce 0. And we don't really need to put t0, right? I mean, t0 is t0. So we don't really need to. I mean, you could if you want to, but you don't really need to. And then here, you know, we want the puck and Bruce to be here at the same time. So it's going to be kind of a mess, right? Oh well, that's life. So we want x puck 1, velocity puck 1, acceleration puck 1, and time 1. And the same point is x Bruce 1, velocity Bruce 1, a Bruce 1, and we already don't know what t is. Okay, now you might think, Brother Weber, you're sure wasting your time. Well, I agree. You kind of want to get in this habit though, x, v, a, t. But I didn't really have to do the a, because I already know from my motion diagram that a is 0. So that was kind of a waste of time. Oh, that's all right. Didn't hurt. All right. Okay? All right. All right, so we got our beginning point, beginning for the puck, beginning for Bruce, and we have our final point. And nothing changes between the initial and the final, so we don't need any more points. All right, so that's the first thing, right? Just label. So this is basically all right, so we label our points. X, V, A, T. That's all you need. Now, everything we have written here, we have to define. So let's do that. Okay, we said this was our origin, so we know that x p0 equals 0. So we're just going to go through it, you know? Just go through it, make sure everything's defined. All right, now what is v puck 0? Well, v puck 0, let's see, that's what we want, right? It says, what speed should you shoot the puck down the ice so it reaches Bruce? So that's what we want, v puck 0. So what I do, I just do this, because then I know when I'm doing my math, that's exactly what I'm looking for. So it's just easy for me, you know, it's right there. Okay, then t0, well, come on. t0 is 0. It doesn't have to be, and in fact, we'll have some problems where it's not, but usually it is. Okay, so I got it, right? I get everything I needed. And I already had my a is 0, so I don't have to bother writing that again. Okay, now let's go to this one. So x Bruce 0. What is x Bruce 0? Well, let's see. All right, so Bruce is 5 meters. Okay. All right, but that's 5 meters from the blue line, right? So you know, this is 5 meters, right? Okay, but we want it relative to the origin. Well, let's see. U, in other words, the puck is 20 meters from the blue line. So this is 20 meters. All right. So what's the position of Bruce relative to the origin? 15, right? 15. So, you know, yeah, you might have to do, you know, some simple things like that. So x Bruce 0 is 15 meters. Okay, let's see. Bruce is going at 4 meters per second. So v Bruce 0 is 4 meters per second. And I don't need to write t0 because I already put t0. Right, so I'm done that. I'm done that. Now let's do that. Okay, so x puck 1 equals x Bruce 1. And what's that? What's the distance from the origin? 20 meters. 20 meters. Okay, I got the x's. Now, velocity puck 1. What's velocity puck 1? Well, it's the same as velocity puck 0, right? It's ice. The velocity doesn't change. So velocity puck 1 equals velocity puck 0, which I don't know, right? which I'm going to find out. Okay, T1, I don't know what T1 is. So T1 equals question mark. And it's a good idea to write this because we'll see later on that we'll have problems where you want to get that, but in order to get that, you have to get that first or something like that. We'll do that later, don't worry. Okay, so I get my XP1, I get my VP1, I get my T1, okay, X Bruce 1, I got my X Bruce 1 already, VB1, so what's VB1? So VB1 is VB0, which is just 4 meters per second, right? Because Bruce doesn't change his speed. All right, let's see, did I do everything right? Let's see if I did everything right. Yeah, I did everything right. Okay, I promise you, I'm going to say this over and over again. I promise you, if you do this right, you have like a 99% chance of getting the problem right if you can do simple math. This is the key, honestly. Okay, now, we haven't had the equations yet. That's chapter 2. So this is all we're going to do in chapter 1, okay? But honestly, you learn how to do this, you'll fly through the equations. All right. Okay, so there's the book, all right? So the puck, initial, Bruce initial. See, if you want to draw the thing, go ahead. I don't bother, you know. Yeah, okay. So what Randy Knight does, he puts known, find. I just put it all here and I put a circle. Whatever you want to do, but just, you know, do it something like this and you'll be great. Okay, so again, first thing we did is we modeled. We said, hey, ice, as far as we're concerned, it's really good ice, so there's no friction, okay? Second thing we did is we drew the motion diagram to help us figure things out. We figured things that A is 0 here, A is 0, Bruce is over here, the puck's over here, you know, constant velocity, the whole bit. So then we drew the pictorial representation, all of this stuff. The most important part, all of this stuff. And we'll learn how to do this next chapter. It's a piece of cake. It's algebra, simple algebra. And then we're just going to make sure that our answer is reasonable. So that's all there is to it. Okay, now let's talk about units. I've mentioned this, but I want to talk about it more. Units. When I talk about units, I'm talking like meters per second or kilograms or something like that. Units. And in this class, we're going to always use, well, most of the time I should say, most of the time we're going to use metric system. All right, and we're going to use what's called the MKS system. Meters, kilograms, seconds. There's other systems like CGS, centimeters, grams, seconds, but we're going to use MKS, right? Meters, kilograms, seconds. And again, you always treat the units, or the dimensions, some people call them, as algebraic quantities. So this is what I'm talking about. So like speed, you know, is distance over time, right? So the units, or the dimensions, you know, they have to be, you know, a length. I mean, this is stupid to say that. A length over time, right? Any length over any time. So it could be miles per hour, could be meters per second, could be, I don't know, whatever, you know, but something like that, okay? Something like that. A distance over time. Acceleration. Acceleration, you know, what's acceleration? It's the change in velocity over the change in time, right? So let's do MKS. So velocity is meters per second. Time is seconds. Well, you can write seconds as seconds over 1, right? And how do you divide fractions? You flip and multiply. So this is a meter per second multiplied by a 1 over a second, which is a meter per second squared. Okay? So that's what it is, right? Okay? So it's a meter per second, which is a meter per second squared. And again, when you're doing your homework, you always have to include your dimensions or your units. Here's another example. So this is an equation we'll learn next chapter. X equals VT minus 1/2, plus X, 1/2 AT squared. Okay? So let's do dimensions. So this is a distance, so it's in meters. Well, you know, you can't have a meter equal to a kilogram. That doesn't make any sense, right? You have to have meters equals meters. You can't have apples equals oranges. So this has to be a meter. This has to be a meter, right? Okay, so let's see if it works. So velocity is in meters per second. Time is a seconds. It's a second, or second over 1, whatever. That kills that, you get meters. Okay, this, a half is nothing. Okay, A is meters per second squared. And time squared is seconds squared. So here you have a second squared that kills this second squared. So you have a meter. So you have meters equals meters plus meters. Okay, has to work out that way. So again, this is a great, you'll see as you do this more and more, this will help you to prevent or to catch errors. Okay, oftentimes in physics or in the real world, you know, you have to convert like cubic kilometers to cubic centimeters or who knows what, right? You're converting units. And let me just show you a little trick. I mean, there's different ways of doing this, but I mean, the trick is to multiply things by 1. So let's say you have kilometers per hour, and we want that to be in MKS, meters per second. So let's say I have 2 kilometers per hour, and I want to convert that to meters per second. Well, you know, in math, you learn that if you multiply something by 1, it's okay. It doesn't change anything. So that's all we're going to do is multiply things by 1. And we'll do it one at a time. Let's say we want to get rid of the kilometer. If I want to get rid of the kilometer, I've got to put it on the bottom. But this is supposed to be equal to 1, but I want a meter, right? So 10 to the third meters equals a kilometer. So this here, doesn't look like a 3. So this is equal to 1. So I haven't cheated, you know, it's perfectly legal. And I can get rid of that and get rid of that. So now I have a meter. Okay, now I've got to get rid of the kilometer. Hour. So hour. So how many seconds in an hour? Well, there's 60 seconds in a minute, 60 minutes in an hour. So 60 times 60 is 3,600. So there's 3,600 seconds. So hour kills the hour. So I don't have a calculator with me, sorry. But so what is 2 kilometers per hour? It'd be 2 times 10 to the third divided by 3,600. Okay? So that, whatever that is. All right, so that's how you do it. You just multiply by 1. Anyway. I don't want to talk about that. Okay, so here's a question you had on your math exam. So let's do it. A lot of people got it wrong, even with my hint. It's kind of disappointing, but anyway. What is the volume of an 8 cubic kilometer region of space in cubic meters? Now, I didn't say what's the shape, so you do whatever you want to do, you know. But I'm going to do a cube just because I feel like it. So here's a cube. Or close to it, whatever. Whatever. It's not bad. Okay, so pretend that's a cube. Now, the volume is 8 cubic kilometers. So if it's a cube, it's going to be 2 kilometers times 2 kilometers times 2 kilometers, right? You know, I could have done a rectangle, right? I could have had like a, you know, something like this. Okay, right? Could have been like 8, you know, this could have been 8 kilometers, 1 kilometer, 1 kilometer, right? So it would have been 8 kilometers times that. So it would have been 8 cubic kilometers. This is 2 times 2 times 2 is 8. Kilometer times kilometer times kilometer is cubed. So what doesn't matter, whatever you want to do. But anyway, let's do the conversion part right. So we'll do it in 2 ways. So what's 2 kilometers? It's 2,000 meters. So that's 2,000 meters, that's 2,000 meters, that's 2,000 meters. Okay, so what's the volume? So the volume is 2,000 meters times 2,000 meters times 2,000 meters, all right? Well, that's 8 times 10 to the 9th meters cubed. Okay, that's how that Okay, that's one way to do it. And that's a good way. Nothing wrong with that. All right, let's do it another way. So another way, we have 8 kilometers cubed. We're just going to do it the way that we learned a minute ago. Multiply by 1. So what's a kilometer? So we want to get rid of kilometers. Kilometers up top, we're going to put them on the bottom. So a kilometer is what? 10 to the 3rd meters, 1,000 meters. However, this is a cubic kilometer. So we've got to cube this thing. Well, what's that? What does that equal? Well, the 8's still 8. Here's a kilometer cubed. Here's a kilometer cubed. What's 10 to the 3rd to the 3rd? 10 to the 9th. So 8 times 10 to the 9th meters cubed. Meters cubed. So however you want to do it, you know what most people put for this? Most people said 8 kilometers cubed equals 8,000 meters cubed. See how totally ridiculous that is? I mean, where'd they come from with that? You know, they forgot it's cubed, right? They just saw the kilometer and the meter, but they forgot it's cubed, you know? So you're only off by a factor of 1,000,000. Not a good thing, right? Okay. You don't want to be off by a factor of 1,000,000. Okay, so this is the metric system prefixes. You need to know these. Now, to be honest with you, in Physics 121, you might see mega once in a while. You see that a lot, that a lot, that a lot, that a lot. Maybe use that in Physics 220 or 221, but we don't usually use these. You know, but come on, get with the times. Learn the metric system. All right, let's quit right now.